All right, guys, so here's another good pressure problem. We have a ball under the water. It's a 1 kilogram ball. It has a radius of 10 centimeters. It's released from rest at the bottom of a 2-meter deep pool of water. We want to know the velocity of the ball when it reaches the surface of the water. That S should not be there. And we want to know how high above the water the ball will rise. So here's what we've got to think. Let's first of all go to a slide where we have some room. First of all, we know that the mass of the ball is 1 kilogram. Which means the weight of the ball is 9.8 newtons. That acts down. We need to know the buoyant force. We need to know the force that acts upward. If we know the buoyant force, we can compare that to the weight and we can find the net force. And from there we can get the acceleration. And that will help us find everything else we need. Before we can find the buoyant force, we need to know the weight of the water displaced by the ball. And before we can find that, we need to know the volume of the water displaced. So the first thing we need to do is find the volume of the ball. For a sphere, this is the equation for the volume of a sphere. This problem gives us the radius of the sphere, 0.1 meters. So we're going to say volume equals 4/3 pi times 0.1 meters cubed. So if we do the math on that, let's cube the 0.1 times pi times 4 divided by 3. And we end up with volume of 0.004. And in this problem we have just two significant digits, so we'll say 0.42 meters cubed. That's not only the volume of the ball, it's also the volume of the water displaced by the ball. It's all the way underwater. We need to know the weight of this much water. So we're going to go to our weight density equation. We're going to solve for weight of water displaced. So we're going to plug in our weight density of water, 9,800. We're going to multiply that by the volume of our water displaced, 0.0042 meters cubed. And we're going to end up with a weight of water displaced of 41.2. That's not only the weight of the water displaced, that's the buoyant force. Now here's what we know in this problem. We know that we have a weight of the ball, 9.8 newtons, that's acting down. We have a buoyant force of 41.2 newtons, that's acting up. So if we subtract those two, that leaves us with a net upward force of 31.4 newtons. Remember, that's an upward force. So now we can calculate acceleration using Newton's second law. A equals F net divided by m. So in this case, we've got a net force of 31.4 newtons, a mass of 1 kilogram. So we end up with an acceleration of 31.4 meters per second squared. Now that's an upward acceleration. Now before we go any further, remember what we know. We know the volume of water displaced, which is also equal to the volume of the ball. We know the weight of water displaced, which is also equal to the buoyant force. We compared that upward buoyant force to the downward weight. We calculated a net force, 31.4 newtons up. We then used Newton's second law, most important idea in physics in my opinion, to calculate the acceleration. And we came up with an acceleration of 31.4 meters per second squared up. Now we're going to go to a blank slide, remembering our acceleration of 31.4. Also remembering that we started off with a ball underwater. And that ball was 2 meters under the water. Started off with an initial velocity of 0. We want to find, first of all, the velocity when it gets here to the top of the water. To do that, we're going to use VF squared equals VI squared plus 2A delta X. And we're going to say VF squared equals 2, our initial velocity of 0 squared, plus 2 times our acceleration, 31.4, times our displacement, 2 meters. Solve that out for VF. We end up with a final velocity of positive 11.2 meters per second. Now the other part of this problem was to figure out how high above the water does the ball go, because it's going to shoot up out of the water. Here's what we know. We know that ball leaves the water with what we're now going to call an initial velocity of 11.2 meters per second. The ball is going to go up to some height where it's going to stop. We're going to call that VF. Once it leaves the water, the acceleration of the ball is gravity, negative 9.8. And we want to find the delta x. So again, we're going to go back to our kinematic equation. We're trying to find delta x, so let's solve that out for delta x. Plug in our variables. So we end up with a final velocity of 0 minus an initial velocity of 11.2 squared, all divided by 2 times the acceleration due to gravity. If we do the math on that, and we do it correctly, let's square 11.2, and then divide that by 19.6. Notice our negative signs are going to cancel. So we're going to be left with positive 6.40 meters above the water. That's our displacement. Hope that helps.